Okay, let's talk about something called constrained extrema. So constrained minima and maxima is what we're doing here. Okay, let's talk about what this is. Optimize z equals cap f of xy subject to the condition that f of xy equals c. So here's the idea. My x and y values are constrained to this assumably smooth level curve, okay? So maybe that's a circle in the plane, or maybe an ellipse, or a hyperbola, or a line, or something like that, okay? So a little f of xy equals c is some sort of level curve, and I'm forcing my x and y values to lie on that curve, okay? So we'll assume that's a level curve, and then it's smooth. Okay, so well-defined tangent line to each point on the curve. Anyway, and now this up here, z is a cap f of xy. Well, I'm going to assume that's cap f is nice and differentiable, so that this is what, some nice smooth surface in 3 space. So do you see what I'm doing? I'm trying to find the high and low points on that surface that are actually constrained to lie on that level curve. Okay? Another way to think about this, if I was to think of these together in 3 dimensions, okay, you'll notice that the level curve is missing z, right? Okay, if I was to imagine actually the set of all points x, y, z in space that satisfy this second condition here, or I should say that's really the condition little f of xy equals c. And since z is missing, if I was to imagine the set of all points x, y, z satisfying that, I would actually have that level curve extruded in the z direction, giving me what? A cylinder in 3 space. Do you see? Okay, that would be a cylinder in 3 space if I was thinking of both x, y, and z. Okay, now that cylinder would intersect this surface, assumably, in some places, okay, giving a nice smooth curve, okay, and I want a nice smooth curve embedded in that surface in 3 space, and I want to know the high z points and low z points on that curve in 3 space, okay? So it would be like trying to find, what would be an analogy? Kind of like trying to find the high and low points on a roller coaster, okay? Okay, where if you took the roller coaster and projected it down into the xy plane, you get this level curve here, okay? I hope that makes sense to you, okay? What would be a concrete example of something like this? Find the local maxima and minima of z equals cap f of xy is just x plus y. Now you can see right here, if I was to graph z equals x plus y, I would end up getting what? I would have a plane in 3 space, right? Okay? And now it's subject, however, to this condition. Notice here, without being subject to this condition, there are no high or low points on this thing, right? That's a plane, and it's certainly not a horizontal plane. You could easily find a normal to that plane, right? About 1, 1, negative 1, right? That's not going to have any maxima or minima points with regard to z at all, okay? But wait a minute, if I subject x and y to the condition that they have to lie on this curve right here, x squared plus y squared equals 4, then maybe there is hope for high and low points on that. Okay, in fact, there are high and low points on that. What is that level curve, by the way? That would be what? The circle centered at the origin with radius 2. Okay, and so the idea is, in terms of the cylinder idea I had before. So let's say here's my plane here. This is z, is x plus y. I don't know how good this looks, but here's the idea. All right, that doesn't look flat, but it's supposed to be a plane. And then what? I'm just considering values of x that lie above this. So if I imagine this being extruded in the z direction, okay, I would end up as a point of intersection here. I would have this kind of ellipse looking thing. in space. It's got some tilt to it here. Let's see how this looks. Okay, and I'd be looking for the high and low points on this fellow right here, this thing. Okay, just sort of give you an idea of what I'm talking about here. Alrighty, all right. Now here's what we're going to do. Let's come back up here to the more general situation here rather than that specific one. Okay, I'm going to imagine that that's a smooth level curve, and I'm going to also imagine that I've actually parameterized it with respect to some parameter, in this case arc length. We can always do that, right? Okay, so I'm going to actually have this, our curve actually has been parameterized by S, okay? So the x and y values satisfying this are a function, or functions I should say, of S, okay? Now I'm interested in high and low points, maximum and minimum values of z, where z is cap f of x, y, but only at those places, at those points on the level curve. So I could think of this way: take those points where that lie on the level curve, right? Here's my level curve, here are the points, okay? They're functions of arc length, okay, so from some fixed points on the curve. And then I'm going to do what? I'm going to take those points and I'm going to evaluate the function at those points so that I now have z as a function of s. So my x and y values will actually be functions of s now. Okay? So this is effectively constraining x and y in theory, right, to points on that level curve. Okay? Now, if I have a function, a nice differentiable function of s here, okay, and I want to find its high and low points, what do? You take its derivative with respect to what? The variable, the independent variable, and set it to 0. So what I would be doing is this. I would differentiate cap f evaluated at x sub s, y sub s, and differentiate with respect to s, and then set that to 0. Okay, so that's just what? That's just Calc 1. Okay, so you know how to do that. Okay, now this is completely theoretical, okay, but it's still going to be useful, as we're going to see here. I say that's completely theoretical because quite often it's hard to parameterize, right, the level curve in terms of arc length from any particular point, but it's a good theoretical parameter. By the way, this example here, right there, of the circle centered at the origin, a radius 2, it could actually be easily done in that case, right? Okay, that would be quite easy in this case. Okay, but usually it's not. Usually it's more theoretical. Okay, but that's okay. We're going to use it in theory here, and we're gonna make progress here. Believe it or not. Okay. Now, first of all, you see this is a function of a function here, right? We need what? This is cap f is a function of two variables. On the other hand, the x and the y are functions of a single variable here. So we're going to need the chain rule here when we talk about this derivative here. Now, that's a whole derivative then. So use the chain rule. So this would be what? F sub x evaluated at x of s, y of s, times what? Dx over ds, which I wrote with the prime notation, plus f sub y at x and y of s, times y prime of s, and that's supposed to be equal to what? 0 there, so I've got that set to 0. Now I'm going to rewrite this in a form that's a little more convenient here. Do you notice here that this is actually what? F sub x, f sub y. Now I'm evaluating at those at points on the curve here, but notice that that is actually the gradient of cap f evaluated at x of s, y of s, okay, dotted with what? X prime of s, y prime of s, okay? If I take the dot product of these two, I get precisely what I have above here, right? Okay, and that's supposed to be what? 0. Now, let's see what this implies here. This would imply, since their dot product is 0, we're just dealing with two space here. Remember, in the xy plane here, okay? Yeah, f is in I mean, now f is just a function of x and y, which are in terms of function of x. Okay, that's why I'm saying these are just functions of two variables here. Okay, the gradient of f is in two dimensions, right? F sub x, f sub y. It is orthogonal to t prime of s. You recognize this from previous chapter, that's actually t prime. That is the what? Unit tangent vector to our level curve at the whatever point we're talking about on that curve. So that's x prime, y prime of s, okay? And since their dot product is 0, what does that mean? It means these two vectors, this vector, the gradient vector, and t hat here, did I say t prime? I said t hat is what I should have said. They're orthogonal to each other because their dot product is 0. Okay? All right, so I'm just going to consider that. Okay? Now let's come back here to our level curve. Okay, let me throw this in here. Okay, remember we had this in theory parameterized with s? That's all that's saying then, right? Now, let's go ahead and differentiate with respect to s on this, and we would have what? This is always going to hold here. So this is actually an identity. Okay, so I differentiate each side with respect to s, and I should get that what? F sub x, x prime, plus f sub y, y prime is equal to 0, since the derivative of c is 0. Okay, and this would hold at each point on the curve. Again, I can write this as a dot product also. Okay, so this is again for points on that curve. Okay, so this is just saying what? Something you already know, that since their dot product is 0, and this is notice this is once again, that's what? That's our t hat. Okay, this is just saying what? The gradient of f is normal to the level curve. We already knew that. Okay, we already knew that. Okay, but it's just saying it again. Now let's put these together though. Okay, del of little f is orthogonal to t hat. Del of cap f is orthogonal to t hat. How can these two vectors both be orthogonal? Into space, remember. How can they both be orthogonal to t hat? How can they both be orthogonal to t hat? Now that's a unit vector. That's not a zero vector. You're not going to get away with something like that. How can these both be orthogonal to t hat, though? They have to be what? In two space, they would have to be parallel, right? All right? Vectors in two space parallel to this, or orthogonal to the same vector, the same unit vector, would have to be parallel to each other, or scalar multiples of each other would be another way to say this. It could be that one of these is actually 0, okay? Maybe both of them. That's kind of trivially orthogonal. Okay, but anyways, here I say it. They are orthogonal. Now, this is only happening at stationary points on the curve. This always happens. This always happens, this part. That's always happens. But this point, this place up here, this is happening only at stationary points, right? This is only at stationary points on the curve. When I say stationary points, places where this holds, right? Maximum and minimum values, possibly other types of points also, but any place where the derivative of cap f with respect to s at points on those curves is 0, okay? All right. Here's another way of saying it then. Okay, I said this already. In two space, two curves are parallel. What does that mean? Okay. Well, I guess it would mean in any space. By the way, when I say parallel, that might be anti-parallel too. Okay. And in any case, they're multiples of each other, right? They're going to be multiples of each other. So we write this. We're just tradition. We say the gradient of cap f is lambda times the gradient of little f, okay? This lambda, this number here, relating these two, what, gradients at stationary points, is called a Lagrange multiplier. Actually, I think this is actually not a cap g. They're not separated. I think that's a little g if memory serves. I should change that there. But that's lambda. Lambda is a Greek L, so Lagrange, right? Okay, you don't have to grow so be so pretentious like I'm in. You can say Lagrange. Okay? Don't say Lagrange, though. That's just making a hash of it. Okay? Let's go ahead and talk about an actual application here. Find the stationary points in the first quadrant that lie on the hyperbola xy equals 4. Okay? So this is our constrained curve, right? The points have to lie on xy equals 4. Okay, now you could graph that on Desmos or something. Okay, it's easy to visualize in your mind, probably. All right, and here's our objective function. Z is cap f of xy is 12x plus 3y. Another plane, right? Okay, well, how do I work this problem? Okay, well, we'll go ahead and do it. We're going to start like this. We'll find the gradient of cap f. That's easy. Okay, so you differentiate cap f with respect to x, then with respect to y. That's very easy. Okay, x and y are independent variables, so we get what? 12 and 3. Okay, what's the gradient of little f? Our little f should be probably what? xy, and then what? Our c is 4. Okay, so we'll go, the gradient of little f would be what? Differentiate xy with respect to x first, and you would get what? Y, and then what? Differentiate with respect to y, holding x as constant, and you get x. Okay? Alrighty, so we have our gradients worked out here. And then what we're going to do is set up the equation here. Remember, at stationary points, this guy should be what? A multiple of this guy. Okay? So we'll say the gradient of cap f is lambda times the gradient of little f. Okay, so now there's what? There's 2 components to these. So what I'm really saying is what? 12 is lambda times y, and what? 3 is lambda times x. Okay? Now what I can do is actually, in this case, solve for y in terms of lambda and x in terms of lambda. Okay? Notice what we've actually lost here in this relation. I should have mentioned that up here. You're going to have to introduce, this is true that these hold at points on the curve where you've got stationary points, but you have to introduce one other fact again at the end here. You have to reintroduce the fact that xy is equal to 4. Okay? This alone is not going to give you, the values of x and y that you need. Okay? See, because I have this loose perimeter. This is 2 equations and 3 unknowns, you see. Okay? Let's not forget then, introducing that constraint, like I just said, xy is equal to 4. So if y is 12 over lambda and x is 3 over lambda, then I could just make those substitutions. And I've got 3 over lambda times 12 over lambda is 4. And I could solve for lambda. And lambda ends up being plus or minus 3. Okay, so there's 2 possible values of lambda here. Now I'm going to back substitute these. Okay, oh, here's one thing I forgot to mention here. Find the stationary points in the first quadrant. Okay, all right, because if I come back here and let lambda be a negative number, well, let's go through this. Let's say lambda is 3, okay? Then substituting on our formulas for x and y, we would get what? X is 1 and y is 4. Okay? Alrighty? Now, if lambda is negative 3, then we would get negative values for x and y. That would not be in quadrant 1, so we're not interested in that. Those points wouldn't be in the first quadrant. So we're not saying we don't have high or low there, but we're not interested in it. Okay, only first quadrant points. Okay, so that's the only stationary point. Now notice that one thing I did not do was actually discuss whether this is what, a maximum point or a minimum point. Now I have my PowerPoint presentation that I'm going to give you, and you guys go ahead and read through that. I'm going to talk about a second derivative test for stuff like this. It's rather complicated. That's why we're not going to use it very much. but it does work here. By the way, something you might do here, actually evaluate the function at the stationary point, and I got 24. Okay, so the value of the function is 24 at either that high or low, we don't know which. Now let me show you a different method here. This is something I'm really going to be using a lot rather than the Lagrange multiplier method. Okay, now I called this the cross product method. I want you guys to know this. I'm actually going to use this in context using decimals. This is the more powerful method, really, than using Lagrange multipliers. Notice that this problem was set up just so you could solve for what? It was really easy solving for x and y in terms of lambda, and then writing a single equation in terms of lambda, right? That's not always going to be the case in the real world. Here's another situation I would like you to consider there. Do you see that we were talking about these two vectors, the two gradients, gradient cap f, gradient little f, being what? Parallel to each other at stationary points? But do you remember two vectors are what? Parallel. Again, you can consider some degenerate cases where you've got zero vectors. But these are going to be parallel, what? If and only if, then, their gradients have a cross product of 0, being the 0 vector. Okay? Do you remember two vectors are what? Parallel in 2 space? That means their cross product is what? 0. Okay, two vectors parallel in 2 space. Their cross product is going to be 0. Okay? By the way, since you're just dealing with two vectors here, okay, vectors in 2 space, in other words, when I go I, j, k, when I take the cross product, okay, so this is a different way of working at here. I'm going to have what? F sub x here, f sub y, 0, okay, and then the little f, okay, same thing, okay. Do you notice that only the k component appears when I take this cross product? Okay, so I actually end up with this. It actually ends up being this determinant times k, the subdeterminant here, and I want that to be the 0 vector. It's this subdeterminant here, where I've got f sub x, f sub y with the cap, and then the little f sub x, f sub y. And you see the only way this is going to be the 0 vector is if what? Since I've got that k component there, the only way that's going to be the 0 vector is if that determinant is 0. Now that's going to be the scalar 0, no bar on it, right? The scalar 0. So let's try it using this method. So I'm going to talk about this, this determinant method instead, this gradient method, if you want, cross product method. Okay, all right, let's do it. There's my two gradients again. Okay, so I'm not going to introduce a lambda at all. There's my two gradients, and I'm going to set that to 0. Now, this was my old notation. But if you don't like it, it's I, j, k. Okay? Quiet down, I'm trying to lecture. Okay? Now, you guys can see what this really means is, with the cross product, 12x minus 3y is equal to 0. That's what this boils down to about. Okay? And then maybe an easier way to say that is what, say maybe y is 4x. And then back substitute that into our, so that gets one relationship between x and y. Don't forget you still have that constraint. And then what I'm going to do is replace y by 4x. So I've got x times 4x is equal to 4. Y is plus or minus 1. And then, or x is plus or minus 1. Y is plus or minus 4 respectively. But we get rid of the negatives because we're sitting in the first quadrant. So we get the same answer we got before, 1, 4. Okay, well, I hope you understood that. Together with my discussion in the PowerPoint, this should be helpful, and with your reading, I'm going to have one more on this topic, one more video, that is. Okay, anyways, I hope this helps.